Hey guys, welcome back to General Chemistry. Today we're going to talk about dimensional analysis again, but we're going to apply it to chemistry. So using some of the chemistry terms that we'll be using for the entirety of the semester. So the first thing I'm going to introduce is this thing called counting numbers. So counting numbers are something that we use in everyday life, and we don't actually have to think about it much. But we're going to apply this concept to chemistry. So counting numbers. If I say I have a pair of dogs, how many dogs do you picture? If I say I have a pair of pears, how many pears do you picture? If I say I have a pair of penguins, how many penguins do you picture? Well, yeah, you're probably going to picture two, right? So the word pair is a counting number, and pair is the same thing as two. We can use that word to count anything we want to count. Another counting number we use quite often is the counting number dozen. So this recipe calls for 1 dozen eggs. It is not explicit about how many that is, but we know that it calls for 1 dozen eggs, so we're going to use 12 eggs. So a dozen is also a counting number. If I said I have a dozen dogs, how many dogs do I have? Yeah, I would have 12. If I said I have a dozen penguins, how many penguins do I have? I've got 12 penguins. So that counting word dozen typically gets used for things like eggs and muffins, but we can use the word dozen to count dogs. Another counting number that you're probably not terribly familiar with, but I think you could probably pick it up pretty quickly. Gettysburg Address said 7 years ago. So score, probably not a counting number that you throw around often. But if I tell you that score is a counting number and it means 20, it means 20 when they said 7 years ago, well, how many years ago were they talking about? So 4 times 20 would be 80 plus the 7, so 87 years ago. I could use it score to count dogs, right? If I said I have a score of dogs, how many dogs do I have? I've got 20. If I have a score of socks, how many socks do I have? I have 20 socks. So score is also a counting number. One you're probably not familiar with, but could pick up pretty quickly. Okay. So let's think about some of the numbers that we're going to be using in chemistry. So let's say the safety pin is made up of pure aluminum. It's just an aluminum safety pin. How many aluminum atoms would fit on the very tip of this pin? Not a trick question. So it's the last number, right? So that is a ridiculously big number, and that's just the tip of this pin. That's not even the whole thing. Okay. So let's see if we can use some of the counting numbers that we talked about to reel in and make that number maybe a little bit more user-friendly. So if we talk about how many pairs of atoms that would be, still lots of zeros. If we talk about how many dozen atoms that would be, still a ridiculously big number. And if we talk about how many score atoms that would be, man, that number just isn't getting any friendlier, right? Still lots and lots of zeros to count. So it seems to me like we need a new counting number. We need something that would reel in our really big numbers in chemistry, make them a little bit more user-friendly. So the counting number that we have is the mole. So the mole is a counting number. If I say I have 1 mole of something, that is 6.022 times 10 to the 23rd of that something. Okay, you see where this is going, right? If I say I have 1 mole of dogs, how many dogs do I have? Yes, I have 6.022 times 10 to the 23rd dogs. If I say I have 1 mole of socks, how many socks do I have? Probably enough socks to fill up the building that you're sitting in, right? So I have 6.022 times 10 to the 23rd socks, okay? So the mole is just another type of counting number. It is 6.022 times 10 to the 23rd. Well, this number has a special name. It's called Avogadro's number. So you may hear me refer to it as Avogadro's number. Now, what are some of the things that we count in chemistry? Well, we don't count things like dogs, unfortunately. So the things that we count in chemistry are going to be things like atoms and molecules and particles. So when I talk about how many atoms do I have, we might use the mole to reel that in. Or if I say there's this many atoms in my sample, I want to make that a user-friendly number, let's get that to moles. So those are the types of things that we're going to be counting and using this Avogadro's number for. Okay. So as you saw on the previous slide, I very strategically wrote out Avogadro's number. So I wrote it out like an equality. We saw equalities when we were first introduced to dimensional analysis. So we thought things like 1 inch is 2.54 centimeters. 1 kilometer is 0.621 miles. So we've seen equalities before. The one wrinkle or new thing about this equality is the unit on the 6.022 isn't a permanent unit, right? So before we had inches to centimeters or kilometers to miles, and those were always the same. Here, our unit can change. It just depends on the problem. If the problem's asking about atoms, this unit right here would be atoms. If the problem's asking about molecules, this unit right here would be molecules. So that unit can change, but the problem's going to dictate that for us. With any equality, we can write it as a conversion factor. So mole on top, Avogadro's number on the bottom, Avogadro's number on the top, mole on the bottom. So here in this picture, we see some samples. The reason I like to put this picture up is because it shows you how crazy these numbers can get very, very quickly. So in each of these pictures, I have weighed out 1 mole of a substance. I know there's grams in the picture. We'll relate that in just a minute. But if we think about how many atoms are in each of these samples, there are 6.022 times 10 to the 23rd atoms in every single one of these pictures. So we're talking about little tiny samples of material in the chemistry lab. Huge number if we were talking about the number of individual atoms. So let's dive into an example. How are we going to put these equalities and conversion factors to practice? So here's our question. How many atoms are in an elemental sample of 22.9 moles of mercury? Okay. So this is really just a dimensional analysis unit conversion problem. I'm starting in the unit of mole, and it's asking me to convert or change the unit to atoms. So it's just simply a unit conversion. So what are we going to do for every dimensional analysis unit conversion problem that has ever existed? We write down the information that's given. So the first thing I'm going to write down is 22.9 moles of mercury. I'm going to draw my train tracks. With little to no thought, the unit that I started with is going to go diagonal or go on the bottom. So I'm going to put moles of mercury down here. Oops. And on the top is going to be my destination. So here I might have to look back at the problem. Where am I going? Yeah, I'm going to atoms. So atoms of mercury on the top. Okay. My units have guided my problem. I'm ready to rock and roll. So I need to peek back at my new conversion factor, or my new equality. Eventually, you'll have this memorized, and so you'll need to know it on the test. But for right now, we can look back at it, peek back at it. What number is attached to mole? Yeah, the number 1. So 1 for now is always going to be the number that's attached to mole. So I click forward to my problem and I see mole is on the bottom. So the number 1 is going to go with that. And in this case, my things in the problem, it was asking about atoms. So that's going to be the unit on Avogadro's number. So 6.022 times 10 to the 23rd is attached to atoms. Good. Okay. Now, we are going to multiply across the top and divide by the bottom. So we're going to take 22.9 times 6.022 times 10 to the 23rd divided by 1, and my calculator spits out but what do I need to consider? Yeah, got to consider sig figs, right? So remember, we always go to this first quadrant. We always go to the original measurement that was taken. So the original measurement had 3 sig figs. So my answer is going to be limited to 3 sig figs. So the answer is 1.38 times 10 to the 25th. And remember, to get our full credit, we're going to have to think about the unit. So the unit of moles canceled, and we got to our unit of atoms of mercury. Okay. Does this answer make sense? Well, we probably aren't terribly familiar with how big a mole is, right? But does it make sense that if we were to measure out some sort of sample of mercury, that would be a ridiculously big number of atoms? Yeah. When we're talking about atoms, usually the number is going to be ridiculously big. So this answer does make sense to me. Here's another example. We're just going the other way. So why don't you pause the video and work it out, and then play the video, and I will show you how I would solve this. All right, how many moles are contained in a sample of 5.95 times 10 to the 22nd atoms of Einsteinium? So what's the first thing that we're going to do for every unit conversion problem that ever exists? We're going to write down the information that's given. So I'm going to write down the 5.95 times 10 to the 22nd atoms of Einsteinium. Okay. Next, I'm going to write atoms of Einsteinium on the bottom. So with little to no thought, that's going to be the unit that I get rid of. And now I'm going to peek to the top and see what my destination is. So it's asking about moles. So up here is going to go moles of Einsteinium. All right, now we need to go back and think about our new equality. So our new equality, 1 mole equals 6.022 times 10 to the 23rd things. In this case, our things again are atoms, right? So on top, I see moles of Einsteinium. The number 1 will always stay with mole for now. And then for atoms, we see that 6.022 times 10 to the 23rd goes with atoms. Multiply across the top, divide by the bottom. So 5.95 times 10 to the 22nd divided by, programming note, When you type this into your calculator, put it into parentheses. The order of operations will mess up if you do not. So, divided by parentheses, 6.022 times 10 to the 23rd, close parentheses, and the answer that spits out is as follows. Oops. Okay. Again, we need to think about or consider significant figures. So we always go to this first quadrant, and I see that there are 3 sig figs. So when I report my answer, I can report 2, just 3 sig figs, and that is moles of Einsteinium. That is your introduction to Avogadro's number and the mole. We'll continue this discussion in the next video. I hope you guys found this helpful.